As Emory students, many of us take different shuttles every day. Our group recognizes wait time as an issue as many students complain about waiting too long for shuttles, particularly at peak times. Thus, we create an optimization model that minimizes wait time by changing the number of shuttles operating at different times of the day in hourly increments. Here is the interface. First, the user can click this button, which shows a form where the user can input the demand for each time interval. The user needs to input demand, whether that is historical data or forecasted data. Additionally, the user needs to input bus capacity, hourly cost of operating the bus, single trip time, which is the amount of time the shuttle takes to make one loop, and the daily budget for operating the shuttle. The user can then use the results from the model to plan the frequency of shuttles moving forward. To save time, we have inputted the data for the loop, which we acquired from the transportation and parking services. Then the user needs to press Save Data so that the data will be inputted into the model. Then press Optimize and it will run for a few minutes. To save time, we already ran this model and got the optimized result. If you click on Show Result, the panel will output the optimal number of shuttles operated in every time frame that minimizes total wait time. For instance, if you see 9 p.m. and 10 p.m., the optimized shuttles are 2 and 1, while at 8 and 9 a.m. during rush hours, the optimized shuttles are 4. Now go to original data and you will see that before we ran the model, total waiting time was 5,073.75 minutes. After optimizing, total waiting time reduced to 4,636.25 minutes. By running this model, we reduced total waiting time by more than 400 minutes. On the right, we see a double line graph that compares average passenger waiting time before and after the optimization. The main takeaway from this graph is that during peak hours, namely 8 to 10 a.m. and 4 to 6 p.m., average passenger waiting time was lower than before. We do recognize that there is a trade-off between demand and waiting time. For example, at around 11 a.m. and 8 p.m., the average waiting time was actually longer than before. Now go to Sheet 1. Here in Sheet 1, this is our underlying model that shows all the previous inputs and outputs. The blue cells are the user inputted data, and the orange cells labeled number of shuttles operated, or frequency, is the optimized result. In this model, there are also a few constraints. First, the total budget must be lower than the user inputted daily budget constraint. Maximum capacity, or the total available number of seats, must be greater than the loading count on the left. In order to set an upper and lower bounds for the decision variables, we set the minimum and maximum to 1 and 10 respectively. We also set a constraint that they must be integers since they represent the number of shuttles operating. And finally, at the top, here is our underlying mathematical model that incorporates into shuttle arrival time, inter-person arrival time, and time intervals. Now if you go back to the interface, all in all, you can see that by using this model, Emory Transportation can both minimize students' and staff's waiting time while ensuring budget constraints are met. And this model primarily applies the loop, but by making a few changes, it can also easily optimize other Emory shuttle routes.